we'll see the NDFSM simulator. Suppose we want to execute an NDFSM machine M. One solution is we'll take a NDFSM, convert and simulate. We'll take a NDFSM machine, we'll convert it to DFSM, then we can apply a simulator for that. That is a one way. And for this algorithm, you are going to pass NDFSM as an input. Okay, so NDFSM convert and simulate, it is the algorithm which you are going to call. This algorithm implicitly call what? The NDFSM to DFSM algorithm, which convert given NDFSM to DFSM. Then it will call a DFSM simulator to find out the hard code for the simulator. But as we saw the previous section, the converting an NDFSM to DFSM can very inefficient in terms of both time and space. If M has a k state, it could take a time and a space equal to big O of 2 raised to k just to do the conversion. Then although the simulation after the conversion would take a time equal to big O of the length of W. So to avoid these time consumption, we'll go with the NDFSM to DFSM simulator directly. So we'd like to algorithm that directly simulate an NDFSM M without converting it to a DFSM. So for conversion it will take a more time. To reduce that time, we'll create a simulator which directly simulate a given NDFSM. So this is a simulator for a NDFSM. So it is same as conversion steps you did for a NDFSM to DFSM. So check out this. So here NDFSM simulator. So directly we are passing a NDFSM to this algorithm and a string. Both we are passing as an input for this simulator, NDFSM simulator. So check out the steps given in this simulator. First is declare the set ST. So ST will hold the current state. A set of states from K. It will hold the current state. Next we are going to declare one more set, that is ST1, which ST1 will be built to contain the next state. So ST is contain the current state, ST1 is containing the next state. Next ST equal to EPS of S. So start state reachable from S via epsilon transition. So we are going to take a start state. We'll start from the start state. Then we are going to find the epsilon transition from that start state. Because it is an NDFSM, so it may contain a epsilon transition. So first we are going to check with the epsilon from the start state which all state I can reach. And that states will be the current state for this algorithm. So ST is what? It is a EPS of start state. So once we find the EPS of start state, whatever states I reach, those become a start state for my DFSM simulator. Next, repeat. So we are going to repeat these steps until C reach the end of the file. Until C reach the end of the file. So what is there in the fourth step? Check it out. So first we are going to take one variable, that is small c, which takes the next symbol from a string W. Suppose my W has 5 characters. So first character will be read and it will be stored in a C. Next we are going to check whether C is the end of the file. So whether it reach the end of the file, whether it is reach the end of the string. If it is the end of the string, then we are going to set st1 equal to null. If it is not the end of the file, then we are going to set st1. Repeat the steps which is given in a fourth. So in this we'll repeat this until a c equal to end of the file. So check out the steps in the fourth step. So first we are going to read the input symbol from the W, that will be assigned to a C. Next we are going to check whether C is not equal to end of the file. If it is not equal to end of the file, then you are going to follow these steps. So st1, that is the next state, which the initial value of this is null. Next, for all q belongs to st do. So you are going to, q is nothing but a state here, or you can say the path which you are going to reach from the current state. So for all path belongs to the current state, do this. For all r, So where find all the state reachable from the Q higher transition labeled C. So for all R is nothing but the next state which you are going to reach from current state after reading the input symbol C. So if there is a transition from a Q to R after reading some input character, okay, so there is a transition which belongs to a transition, then you are going to do this. So st1 equal to what? St1 is what? It is a next state. Next state equal to what? The next state itself union the EPS of R. So R is a C. You are going to check the transition from current state for input symbol. So you are going to reach where? You are going to reach R. So once you reach R, that will be your next state. So next state, that is equal to st of 1, that is next state union EPS of R. So once you reach the next state, you are going to check the epsilon transition for that state. So that will be combined and that will be considered as your next state. Okay, so after that you are going to change the current state equal to next state. So whatever the next state value is there, that you are going to assign to a current state. After that you are going to repeat this step. Okay, if st equal to null, then exit. So here st is not a null, it has some state. Then you are going to repeat the next steps. So c equal to get next input symbol from the w. If c is not end of the file, then st1 equal to null. Next, for all q belongs to st. So what is the st value? In the previous step, whatever the state I got, that will be my current state. So if q belongs to s2, then you are going to find the transition for input symbol from q to a next state. Then you are going to take the epsilon transition of that state, and that will be your next state. So you are going to repeat all these steps until c reach a end of the file. So if c reach a end of the file, then you are going to come out of this fourth step. Then you are going to execute what? You are going to execute a fifth step. What is there in the fifth step? If st intersection of a not equal to null, then accept, else reject. So whatever the current state at the end you get, if it has the accepting state, then you are going to say accept. If it doesn't have a accepting state, then you are going to say it reached the rejecting state. Okay, so this is all about the NDFSM simulator. So we'll take one example and see how this works. So here, if example, if I had drawn the DFSM to accept the string. Okay, previous one you consider to accept the strings of A's and B's where the occurrence of B is 1. So this is a valid string, we'll consider this. And the end of the string, always we have a dollar indicate it is end of the string. So we'll take the previous example. So this is my example. So I'm going to write a hard code like this. But here the little bit change I am going to do, I'll find the EPS function from the current state. Then I will check out the transition from each of the EPS states. So first st, declare the st. So st equal to what? It hold the current state. Say it has 0 state. st1, it is a 1 state. It is a null initially. So st equal to EPS of s. So we'll take one example and trace this. So you'll get a correct result. So in the worst case, m is in all state all the time, and each of them has a transition to every other state. So what is the worst case for this? If machine is in all the states all the time and each of them has a transition to every other state. So if the machine has a transition to all other states and all other state have some transition between each other. So the pass could take many of big O of k raised to length of k raised to 2 steps for a total cost of big O of length of w into k raised to 2. So this is the total cost to for the NDFSM simulate algorithm. So this is all about the NDFSM simulators. Next we will move to a minimization of finite state machine. So if you are going to solve a real problem with an finite state machine, we may want to find the smallest one that does the job. So many finite state machine you can create for a current given problem, but among that I want to create a smallest final state machine which solve my real time problems. So we will say that DFSM is a minimal if and only if there is a no other DFSM m dash such that L of m equal to L of m dash. So here L of m and L of m dash are the two machines which accept the same language. But L of m dash is what? It is a minimal DFSM which accept the given string. Okay. So and m dash has a fewer state than the m. So both are accepting the same language, both are the DFSM, but whatever the minimum DFSM I got, which has the lesser state compared to L of m. We might want to be able to ask, given a language L is there is a minimal DFSM that accept the L. If there is a minimal machine, is it unique? Given so once we draw the minimum machines, then many questions come into the mind that given a language L, is there a minimal DFSM that accept the L? If there is a minimal machine, it is a unique. So once we construct the minimum machine, we can say that is a unique one, that is uh, a unique DFSM which is meant for a particular language. Given a DFSM M that accepts some language L, can we tell whether M is a minimal? Given a DFSM, can we construct a minimal equivalent to DFSM? So these all questions arise, and the answer for all these questions is yes. So once we construct the minimum DFSM, that is the final one, which accepts the same language, which is a unique, and the whatever the language accepted by DFSM and the minimal DFSM both are equal. So the construction of building of a minimal DFSM for a language. So an effective way to think about the design of a DFSM to accept some language L over an alphabet was to was to cluster the strings in alphabet star in such a way that strings that share a feature will drive M to the same state. We will now formalize this idea and use it as a basic for constructing a minimal DFSM to accept the language. So we are going to build a minimal DFSM for a given language. So which accept the same alphabets, okay, and which accept the same language. The language is made up of a same alphabet. So here to construct the minimal DFSM, we will come across with two types of states, that is indistinguishable states and the distinguishable states. So we will say that X and Y are the indistinguishable with respect to the language, which we will write as X is equivalent to Y in terms of language if and only if Z belongs to alphabet star. So Z belongs to alphabet star, either both XZ and YZ belongs to L or neither is. So if Z is belongs to the alphabet star, so either both XZ and YZ. See, Z is a alphabet which is there in the alphabet set. So either XZ or YZ belongs to the L or neither. So either X has a Z or a Y has a Z. So because Z is belongs to the language or neither it has. So these are the indistinguishable states. So we will say that the X and Y are distinguishable with respect to L if and only if they are not indistinguishable. So if X and Y are distinguishable, then there exists at least one string Z such that one but not both XZ and YZ are YZ is in L. So we'll see the clear definition of this indistinguishable and distinguishable in the next classes, and we'll see how to construct a minimum DFSM for a given DFSM. So we'll see steps and all that in our next video. So thank you. Go through all this once again. I hope you understood this. Thank you once again.